Imagine lifting your hand before your eyes. You see skin, veins, bone, something tangible, solid, reassuring. Now, imagine peeling back that illusion. Peel away the skin, dissolve the muscle, collapse the bone, and plunge downwards. Past the cells, past the molecules, past the atoms. Keep going. The solidity shatters. Suddenly, your hand is no longer a structure, but a storm. A chaotic swirl of particles flickering into and out of existence. What you thought was firm and unyielding dissolves into emptiness, held together by forces you cannot see. And among these forces lies one of the strangest phantoms ever conceived by human thought, the gluon, the so-called glue of the universe. The invisible hand that binds quarks together, welding the heart of every atom. But here is the question that should freeze your breath. Are gluons even real? Or have we built the entire architecture of reality upon shadows we can never touch? For centuries, the dream of solidity comforted us. The Greek atomists once imagined indivisible seeds of matter, eternal, unbreakable. To them, atoms were ultimate reality, the bedrock beneath appearances. Modern science, with its colliders and detectors, has shattered that comfort. Atoms are not indivisible. Protons and neutrons are not solid beads, but bundles of smaller entities, quarks. And quarks themselves, they never appear alone. No one has ever trapped a solitary quark, no matter how violently we smash the universe apart. They come bound, chained, locked together in eternal confinement. And the supposed chains that bind them are gluons. We speak of gluons as particles, as if they are like photons or electrons, little quanta flying through space. But already the ground beneath us trembles. Unlike photons, which carry light and can be isolated, gluons cannot exist as free particles in the vacuum. They are both everywhere and nowhere, condemned to live only within the prison of quarks. Imagine a jailer that can never leave the cell block, yet somehow keeps the entire structure of matter from collapsing. We infer their presence from the traces left in violent collisions. We write equations that describe them with a terrifying elegance. But we cannot see them. We cannot hold them. And this raises the question, what does it mean for something to be real if it cannot exist outside the walls we imagine for it? Zoom out again, away from the dizzying chaos of quarks, and reality feels firm once more. The chair you sit on does not collapse. The stars continue to burn. The universe holds. Yet every ounce of this stability relies on a dance of invisible forces at the smallest possible scales. Without gluons, protons and neutrons would explode apart. Without them, the nuclei of atoms would disintegrate. Without them, the stars could never fuse hydrogen into heavier elements. You would not exist, nor would your hand, nor the cosmos itself. Reality depends utterly on something we cannot touch. How precarious, then, is this illusion of solidity? Physicists have long wrestled with this paradox. The strong nuclear force, the most powerful of nature's four known interactions, is mediated, in theory, by gluons. They are the carriers of color charge, a property more abstract and haunting than the familiar electric charge of electrons. Quarks come in three colors, red, green, and blue, though these are not colors of sight, but labels of mathematical symmetry. Gluons bind these charges together, ensuring quarks always assemble in colorless trios or pairs. Yet these gluons themselves carry color, and so they interact with one another in a tangled web of self-confinement. Unlike photons, which pass serenely through one another, gluons snarl and twist, pulling tighter the more they are forced apart. Imagine a rubber band stretched. The further you pull, the stronger it resists. In the quantum realm, this resistance grows without limit, until quarks and gluons are forever locked within their tiny prisons. This is the mystery of confinement, and it is why no one has ever glimpsed a free gluon, even in the most violent experiments. The implications are staggering. When you press your hand against a table, What resists you is not atoms, not even electrons, but the hidden authority of gluons. They account for almost all the mass of your hand. The quarks themselves contribute only a few percent. The rest comes from the binding energy of gluons, energy trapped in the ceaseless maelstrom of the strong force. Your very weight is not a property of solid matter at all, but the echo of an invisible glue that no eye has ever seen. What does it mean then to speak of matter as real if its substance lies in forces that cannot be isolated, in particles that cannot be freed? Consider the alternative for a moment. Strip the world of gluons, erase their phantom hands from the equations. Quarks would drift apart like dust in the void. Protons would never form. Hydrogen atoms would unravel, stars would never ignite, the universe would collapse back into a featureless sea of particles. In a very literal sense, gluons are the reason anything exists in the form we know it. And yet, their existence is a deduction, a whisper behind the data, a ghost glimpsed only in theory. The irony is cruel. The strongest force in nature may rest on the weakest evidence of all. Perhaps this is not surprising. Human beings have always built their worlds upon invisible pillars. Gravity cannot be seen, only felt. Time cannot be touched, only measured. And so it is with gluons, constructs that shape our reality from a realm forever hidden. The Greeks once imagined gods pulling the strings of fate. We have replaced gods with equations, but the sense of mystery lingers. Is the glue of the universe truly a particle? Or is it simply a name for the limits of our imagination, a mathematical bandage across the fracture lines of physics? This is the comfort zone we inhabit, the illusion of solidity, of atoms as beads and matter as firm. But already cracks are spreading through this illusion. For when we ask whether gluons are real, we discover that reality itself begins to tremble. Are we clinging to shadows in the void? Have we mistaken the scaffolding of theory for the substance of the world? And if the glue of existence is a phantom, what does that make of everything we hold, everything we are? Because if gluons are not real, then neither is your hand. The standard model of particle physics is often described as one of humanity's greatest intellectual achievements, a compact equation etched into textbooks, capable of describing nearly everything we see in the universe. From the dance of electrons in atoms to the searing collisions at particle accelerators, its predictions have proven uncannily accurate. It is, in a sense, our modern scripture of the subatomic world. And yet, even in this triumph, shadows creep at the edges, for the standard model rests upon entities that strain the very notion of reality, and none more so than the gluon. Unlike electrons or photons whose existence has been demonstrated by direct detection, gluons remain elusive. We cannot bottle them, nor can we allow them to traverse detectors unbound. Their presence is inferred, their signatures stitched together from the aftermath of high-energy collisions. We watch for jets of particles spraying outward, chaotic cascades born from the splitting of quarks and gluons. But what we truly see are the fragments, the debris of something unseen. Gluons appear to us like footprints in sand after the tide has already come and gone, and so, despite their centrality, their reality is not empirical in the everyday sense. They are both the most important particles in the standard model and its most ghost-like. But the unease runs deeper. Even if we accept gluons as indispensable, the standard model itself is riddled with fractures. It explains neither gravity nor dark matter, the mysterious substance outweighing normal matter 5-to-1. It cannot account for dark energy, the force accelerating the expansion of the cosmos. It falters in unifying the forces under one framework. And within this already fragile construct, gluons embody the contradictions most starkly, for they are defined as massless carriers of the strong force, yet through their interactions they generate nearly all the mass in the universe. They are invisible, yet the very reason matter exists. They are prisoners of confinement, yet responsible for the stability of the cosmos. Their paradoxical nature gnaws at the edges of certainty. Physicists cloak this paradox in the formalism of quantum chromodynamics, or QCD. QCD is an exquisitely beautiful theory, describing how quarks and gluons interact through the language of symmetry groups. It predicts phenomena like asymptotic freedom, the fact that quarks behave almost independently at extremely high energies, and confinement, the eternal binding that prevents their isolation. These ideas are not mere speculation. They are supported by experimental evidence, indirect but powerful. Yet the beauty of the mathematics hides the abyss. The gluon cannot be isolated or observed directly. Its existence is a necessity of the theory, not of empirical sight. And so we must ask, do we believe in gluons because they are real, or because without them the standard model collapses? The problem is not without precedent. Science has long entertained entities that proved illusory. In the 18th century, chemists believed in phlogiston, a substance thought to flow out of burning material. Its logic seemed impeccable until oxygen theory replaced it. In the 19th century, physicists believed in the luminiferous ether, the medium through which light waves supposedly traveled. No one ever detected it, and Einstein's relativity consigned it to history. Could gluons too be phantoms of convenience, useful scaffolding destined to crumble under a more complete understanding? For now, the evidence binds us to them. In the particle collisions at CERN's Large Hadron Collider, in the deep, inelastic scattering experiments at SLH, the fingerprints of gluons are unmistakable. The scattering patterns, the jets, the structure functions of protons all point to the contribution of these massless, self-interacting messengers. Without gluons, the data refuses to cohere. The standard model would fall apart like a house of cards, and yet the cracks remain. If gluons are indispensable, why can they never be freed? If their signatures are everywhere, why must we infer them indirectly? If they are so central, why does the theory that describes them fail to illuminate the full cosmos? These are not idle questions. They echo in the laboratories, in the equations of theorists, and in the philosophical undercurrents of science itself. What does it mean to know a particle exists if it can never appear outside the confines of its prison? What does it mean for a theory to be complete if it leaves untouched the greatest mysteries of the universe? The standard model gives us precision, but perhaps at the cost of depth. It explains, but also conceals. It is here that the cracks widen. Dark matter is invisible to QCD. Gluons cannot explain it. Dark energy lies beyond its reach. Gravity mocks its incompleteness. Attempts to stitch the standard model into a grand unified theory have failed, unraveling in contradictions. And still we cling to gluons, because without them we have nothing. The glue of the universe may be as fragile as the faith we place in our mathematics. The tension becomes clear. Are we uncovering truth or constructing a scaffold? Is the standard model the final word, or merely a chapter in a longer story? Gluons embody this tension perfectly. They are indispensable in theory, impossible in isolation, and enigmatic in interpretation. If they are real, they reveal the hidden machinery of existence. If they are not, then our vision of reality is deeply flawed, and the universe may be stranger than even QCD dares to imagine. And so we arrive at the edge of the abyss. The standard model, triumphant yet incomplete, leans heavily on gluons to hold it together. But the very presence of gluons raises doubts that ripple outward. If they cannot be touched, can they be trusted? If they cannot be freed, can they be said to exist? If the strongest force in nature depends on something intangible, what hidden truths lurk beneath the subatomic shadows? Because as we peer deeper into the cracks of the standard model, one truth emerges. The gluon may not be the answer, but the question itself. To truly confront the enigma of gluons, we must journey into conditions where ordinary matter dissolves into something primordial, where protons and neutrons lose their identities, and quarks and gluons swim freely in a state so alien it resembles the first microseconds after the Big Bang. This is the quark-gluon plasma, and it represents our best attempt to force reality to show its hidden hand. In the ordinary world, confinement rules. Quarks are shackled, gluons chained to their perpetual prison. But in the heart of particle colliders, where nuclei slam together at nearly the speed of light, temperatures soar to trillions of degrees. Under these conditions, the bonds loosen. Matter itself melts. Protons and neutrons shatter, and for a fleeting instant, the universe becomes a furnace of liberated quarks and gluons. It is a descent into the abyss where the familiar dissolves and only chaos remains. The Large Hadron Collider at CERN and the relativistic heavy ion collider at Brookhaven are the gates to this abyss. When heavy ions collide, gold against gold, lead against lead, they unleash energies so violent that ordinary matter cannot survive. Instead, detectors record sprays of particles, shockwaves rippling through the medium, and the telltale viscosity of a strange, fluid-like state. Quark-gluon plasma is not gas, not liquid, not solid. It is a new form of matter, hotter than the core of any star, older than time itself. And buried within its signals are clues to the reality of gluons. Physicists approach this inferno with mathematical weapons. Quantum chromodynamics predicts that as energy scales rise, quarks and gluons behave as if freed from confinement. This property, known as asymptotic freedom, is one of the crowning discoveries of QCD. At extreme temperatures, the strength of the strong force diminishes, and quarks glide past one another like dancers freed from chains. Yet this freedom is deceptive, for even here, gluons refuse to stand alone. They interact with one another, weaving a storm of exchanges so intricate that individual particles vanish into a collective blur. The abyss reveals freedom, but only in a form that defies direct sight. Consider the irony. We build colliders the size of cities, spend billions of dollars, and recreate the conditions of the infant cosmos. We summon energies not seen since the birth of the universe itself. And still, gluons evade us. They manifest as flows, as patterns, as ripples in the data, never as isolated beings. The closer we come to the truth, the more it slips away. It is as if reality has built its own defense, keeping its deepest glue forever hidden. Yet in this abyss, revelations abound. The plasma created in heavy ion collisions behaves not like a weakly interacting gas, but like an almost perfect fluid. Its viscosity, its resistance to flow, is smaller than that of any known substance, closer to the theoretical quantum limit than anything else in nature. This fluid is not chaotic in the way one might expect. It is ordered, coherent, flowing with a strange perfection. What does it mean that the most violent collisions produce the most elegant fluid? What does it mean that gluons, though unseen, orchestrate a collective harmony more refined than the most delicate of human creations? The descent also raises a philosophical tension. Freedom, in the human imagination, is escape. Liberation from bonds, the ability to exist unconfined. But in the subatomic world, freedom is conditional, fragile, fleeting. Quarks may move freely only at unimaginable energies, only for moments so brief they defy comprehension. And gluons, even in this liberation, remain entangled, forever self-interacting, never solitary. Is this freedom, or is it simply another kind of confinement? One where the walls expand, but the prison endures. For decades, physicists have pursued the quark-gluon plasma not only to understand gluons, but to confront the earliest moments of existence. To gaze into the abyss is to peer backward in time, to glimpse the universe when it was less than a millionth of a second old. In those moments, the cosmos was a seething plasma, gluons and quarks unbound, a furnace of pure potential. From this abyss, the structure of everything emerged. To recreate it is to hold a mirror to creation itself. And yet, every attempt ends the same, with gluons slipping through our fingers. There are those who argue that this is the true lesson. that the reality of gluons lies not in their individuality, but in their collective behavior. Just as waves are not the water itself, but the motion of water, perhaps gluons are not things but motions, ripples in a deeper field, patterns in an unseen fabric. To seek them as isolated particles may be to misunderstand their nature. Perhaps the abyss is teaching us to look differently, to abandon the comfort of particles and embrace the terror of patterns without end. But the question cannot be avoided. If gluons only exist as parts of a collective storm, are they real? Or are they simply placeholders in our equations, convenient phantoms conjured to make sense of what we cannot otherwise describe? The quark-gluon plasma, with its elegance and its fury, offers no clear answer. It deepens the paradox. It proves the necessity of gluons and simultaneously their elusiveness. The abyss has another lesson. Even as we probe it with colliders and detectors, we realize that our instruments are clumsy compared to the scale of the forces we seek. We measure with machines, interpret with equations, but what we chase is more ephemeral than light itself. The deeper we descend, the more reality mocks us with its refusal to yield. Are we explorers, uncovering truths, or are we prisoners, circling within the cage of our own theories? In the end, the descent into the subatomic abyss is not a triumph, but a haunting. It reveals just enough to unsettle, just enough to remind us that the foundations of existence are stranger than we can bear. We stare into the furnace of creation, and instead of clarity, we find only questions multiplying in the dark. And as we emerge from this plasma, blinking into the ordinary world once more, we are left with a whisper that refuses to fade. If the gluon can never be seen, never touched, never freed, then what exactly are we believing in? Because if the abyss conceals more than it reveals, then perhaps the real ghost is not the gluon itself, but our certainty that we have ever understood reality at all. The search for gluons has never been a straightforward pursuit. Unlike electrons, which leave clear tracks in cloud chambers, or photons, which can be counted one by one in detectors, gluons hide behind a veil of indirect evidence. To hunt them is to chase a ghost, one that shapes the very fabric of matter, yet slips through every net we cast. The story begins in the 1960s when Murray Gell-Mann proposed the quark model. Protons and neutrons, long thought to be fundamental, were suddenly revealed as composites. Quarks explained the zoo of particles emerging from accelerators, providing order where chaos once reigned. But the quark model introduced a problem. If quarks existed, what bound them together? Why didn't they simply fly apart? And why, if they were real, had no one ever observed a free one? To solve this paradox, physicists proposed a new force, stronger than any other known, the strong nuclear force. And with it, new carriers, gluons. They would act as messengers between quarks, binding them together with an exchange force analogous to the way photons mediate electromagnetism. The theory was bold, elegant, necessary. Yet from the beginning, it demanded a leap of faith. Gluons could not be plucked from nature like electrons or protons. Their existence would be forever inferred, never directly witnessed. The decades that followed became a relentless hunt. Deep, inelastic scattering experiments in the 1970s revealed that protons were not smooth spheres but seething interiors where constituents jostled and scattered. The data pointed to more than quarks. Something else inside the proton was carrying momentum, unseen yet unavoidable. The invisible glue was already there, hidden in plain sight, but evidence is not the same as presence. To claim that gluons are real, physicists needed more than indirect hints. They turned to colliders, smashing particles together at higher and higher energies, searching for traces that could only be explained by gluons. At Petra, a collider in Hamburg, scientists found one of the first compelling signatures: 3 jet events. When electrons and positrons annihilated, the collisions produced not 2 jets of particles, as expected from quark-antiquark pairs, but three. The third jet was interpreted as the spray of a gluon, a fragment of the ghost itself. For the first time, the theory found experimental footing, yet even here the triumph was fragile. Jets are not gluons. They are showers of hadrons, secondary particles produced when quarks and gluons fragment into more familiar forms. To see a jet is to see the aftermath, not the act itself. It is like inferring a storm from the wreckage it leaves behind. Convincing, yes. Definitive, hardly. The ghost remained. Physicists pressed onward, developing increasingly sophisticated detectors, algorithms, and simulations. They traced the energy flows in collisions, mapped the distributions of jets, and built mathematical models that matched the patterns. Each match deepened confidence in gluons, yet each also reinforced the unsettling truth. The evidence was circumstantial. We can prove their necessity, but never hold them in isolation. The gluon is real because it must be, not because it is ever seen. This dependence on theory recalls other ghosts of science. Phlogiston, that phantom of combustion, explained fire until oxygen theory displaced it. The ether, once thought essential for light waves, evaporated with Einstein's relativity. Both were compelling, consistent, even elegant. Both turned out to be illusions. The comparison haunts the hunt for gluons. Could these jets and scatterings, however persuasive, conceal a deeper truth we have yet to glimpse? Could gluons be the phlogiston of the strong force, a placeholder awaiting its replacement? One reason for doubt lies in their unique property, self-interaction. Unlike photons which glide past one another untouched, gluons carry color charge and thus interact with each other. This makes them fundamentally different, tangled in a web of complexity. It is a property that gives rise to confinement, the eternal imprisonment of quarks and gluons within hadrons. But it also ensures that gluons will never emerge as free particles, never travel across space as photons do. Their reality is chained to their prison. What kind of existence is this? Consider the irony. The very thing that makes gluons indispensable also makes them invisible. Their self-interaction guarantees the binding of matter, but also guarantees they can never be observed directly. They are both the foundation of reality and its most elusive inhabitants. We are left with shadows, imprints, after-images, the suggestion of a presence that never steps into the light. And yet, the search has not been in vain. The precision of quantum chromodynamics, the theory of quarks and gluons, has withstood decades of scrutiny. Its predictions match experiment after experiment, from jet production to hadron masses. The theory works. It is astonishingly successful. And still the question persists: does success prove reality, or only the usefulness of a model? If we can predict the behavior of the universe with gluons, does that make them real? Or does it only prove that we have chosen the right language to describe something we do not yet fully understand? This is the haunting beauty of science. Each answer opens new doubts, each success reveals new cracks. The hunt for gluons exemplifies this tension. We have not caught the ghost, but we have charted its shadows. We have not isolated it, but we have built an entire edifice of knowledge upon it. We trust in the ghost because without it, reality collapses. And yet deep down, we know the ghost may one day vanish, replaced by a deeper truth. History reminds us to be cautious. The ether was believed in as fervently as gluons are now. Phlogiston explained combustion for over a century. Both seemed indispensable until they were discarded. Could we be making the same mistake? Or is the gluon different? Not a phantom, but a genuine inhabitant of the subatomic world, forever hidden by its own nature. As the hunt continues, anomalies emerge. Data points that refuse to align perfectly, scattering distributions that whisper of something more. Are these cracks in our model, or glimpses of a deeper reality? What if gluons, as we describe them, are not the final word? What if they are only approximations of something stranger, more fundamental, lurking beneath the equations of QCD? The hunt is far from over. Detectors grow sharper, colliders more powerful, simulations more intricate. Each new advance brings us closer, yet also pushes the ghost further away. The more we know, the less certain we become, and so the question deepens: are we chasing a particle or a mirage? Because as the hunt intensifies, one possibility begins to surface, unsettling and profound. What if gluons do exist, but not in the way we imagine? What if they are real, but in forms our theories cannot yet describe? What if the ghost has been with us all along, waiting to reveal itself in ways we have not yet conceived? The deeper we travel into the quantum world, the more we realize that theory itself becomes both our guiding light and our prison. Nowhere is this tension clearer than in quantum chromodynamics, the theory that gives gluons their name, their properties, and their phantom life. For in equations, gluons are not vague shadows but precise entities, massless, self-interacting carriers of the strong force. In mathematics, they are undeniable. In reality, they remain invisible. Quantum chromodynamics, or QCD, is one of the most elegant constructions in all of physics. It is based on the symmetry group SU3, a mathematical structure of rotations in an abstract color space. This symmetry requires the existence of 8 distinct gluons, each carrying a combination of color and anticolor. Unlike photons, which are electrically neutral, gluons are charged with the very force they carry. This bizarre self-reference is what makes the strong force so unique. Gluons interact not only with quarks, but with each other. It is a hall of mirrors, a web of interactions so dense it defies ordinary comprehension. The elegance of the mathematics is undeniable. QCD predicts asymptotic freedom. As quarks are probed at shorter distances, the strong force grows weaker, allowing them to move almost freely. It also predicts confinement. As quarks attempt to separate, the force grows stronger, preventing their liberation. Both predictions have been confirmed indirectly through experiments. The theory explains why quarks are never seen alone, why hadrons form, why the strong force behaves so differently from electromagnetism. In its beauty, QCD seems unassailable, and yet beauty is not proof. Mathematics may be flawless, but does that mean nature obeys it? History offers cautionary tales. The Ptolemaic system of epicycles described planetary motion with extraordinary precision, yet it was built on a false foundation. Newton's laws described the motions of the heavens with uncanny accuracy until relativity revealed their limitations. Perhaps QCD is the same, a mathematical masterpiece, dazzling and precise, but only an approximation of a deeper truth. The role of gluons within this masterpiece is particularly haunting. They are described as massless, yet they generate nearly all the mass in the universe. They cannot exist freely, yet they define the structure of all matter. They are the paradox at the center of the theory, the contradiction around which everything else orbits. What kind of reality is this? A particle that exists only in equations, whose properties are inferred, whose presence is never directly revealed. To understand gluons in theory is to confront the strange duality of physics itself. On one hand, the equations demand their existence. Without gluons, the strong force collapses, confinement disappears, the standard model loses coherence. On the other hand, experiments only ever show us indirect consequences, never the thing itself. The theory holds the ghost firmly, but the world refuses to hand it over. It is here that philosophy enters the equation. What does it mean for something to be real? If a concept is mathematically indispensable, does that grant it existence? Or is it merely a tool, a scaffolding of human thought? Gluons test the boundaries of our definitions. They are not like rocks which can be held. They are not like photons which can be detected. They are not even like quarks, whose presence in scattering experiments can be mapped. Gluons are both everywhere and nowhere, the very definition of theoretical reality. This tension is sharpened by the sheer elegance of QCD. Its structure is not arbitrary but profoundly symmetrical, hinting at a deeper order to the universe. The 8 gluons emerge naturally from the mathematics, not from arbitrary invention. The theory unifies countless phenomena, from the binding of nuclei to the spectra of hadrons. It has been tested and retested, and its predictions have not failed. To doubt gluons, in some sense, is to doubt the very language of physics. And yet physics itself teaches us humility. Every theory, no matter how elegant, is provisional. There is another irony. The very beauty of QCD may blind us. Human beings are seduced by elegance, by symmetry, by patterns that feel inevitable. But nature is not obligated to follow our sense of beauty. It may deceive us, lure us into believing in phantoms because the mathematics is too compelling to resist. We must ask, do we believe in gluons because they are real, or because the equations are too beautiful to abandon? Even within QCD, cracks appear. Calculations become intractable at low energies, where confinement dominates. The equations spiral into infinities, requiring supercomputers and lattice simulations to approximate solutions. The mathematics that defines gluons becomes a labyrinth, one we can only navigate with enormous effort. This is not the simplicity of nature laid bare, but a constant struggle to match theory to experiment. Gluons remain always at the edge of grasp, and so we are left with a paradox. QCD's grip on gluons is both absolute and fragile. Absolute because the theory demands them, fragile because we can never isolate them. They are indispensable and intangible, central and spectral. They are the glue not only of matter but of our own uncertainty. The human mind is uncomfortable with this ambiguity. We want reality to be firm, particles to be real, forces to be tangible. But perhaps the lesson of gluons is that reality is not like that. Perhaps reality is patterns without substance, equations without particles, forces without carriers. Perhaps gluons are less entities than relationships, less things than the very act of binding. If so, then their reality is not in their existence, but in their effect. The glue is not the substance, the glue is the binding itself, and yet the doubts persist. Experiments whisper discrepancies. Lattice simulations struggle to capture the full complexity. The elegance of QCD may be a veil covering a deeper void. What if gluons are not fundamental but emergent? What if they are the shadows of a deeper theory, like strings vibrating in hidden dimensions or fields beyond our comprehension? What if the beauty of QCD is not final truth, but the first step towards something stranger? This is the dilemma of the gluon in theory's grip. We are enthralled by the elegance, yet haunted by the possibility that it deceives us. We are bound by the equations, yet aware that equations can mislead. The gluon, perfect in mathematics, elusive in reality, forces us to confront the limits of our knowledge. Because as beautiful as QCD may be, beauty does not guarantee truth. And if gluons are the most elegant illusion science has ever created, what rifts in our understanding are waiting to tear open beneath us? For all the elegance of quantum chromodynamics, for all the beauty of gluons etched in mathematics, physics is not satisfied with equations alone. Theories must be tested. The universe must be forced to answer. If gluons are real, then somewhere in the data of our most violent experiments, their presence must be undeniable. And so physicists have spent decades trying to seize evidence from the chaos of high-energy collisions, to pull from fire and debris the faintest proof that the ghost has substance. The story begins with deep, inelastic scattering experiments at the Stanford Linear Accelerator Center in the late 1960s and early 1970s. Electrons were hurled at protons with unprecedented energy. Instead of scattering smoothly, as one might expect if protons were solid, the electrons ricocheted as though striking smaller, harder targets hidden inside. These were the quarks, the constituents of protons. But the data revealed something more. The momentum of the proton was not fully accounted for by the quarks alone. Something else inside carried a significant share. That something was interpreted as gluons. Already the fingerprints of the invisible glue appeared in scattering patterns that quarks could not explain, yet scattering alone could not seal the case. Physicists pressed forward, constructing colliders capable of smashing matter into matter at ever higher energies. At Petra, in Hamburg in 1979, electron-positron annihilations produced a revelation: 3-jet events. Instead of the 2 jets expected from quark-antiquark pairs, detectors recorded a third. The explanation was astonishing. This third jet was the shower of particles left behind by a gluon. For the first time, the ghost seemed to manifest. The announcement reverberated through physics. Gluons had been glimpsed. But even this triumph was bittersweet. What Petra recorded was not a gluon itself, but a spray of hadrons produced as the gluon fragmented under confinement. The evidence was indirect, the conclusion interpretive. Still, it was enough to convince many. Here, at last, was a sign that the mathematics of QCD described something more than elegant abstraction. The pursuit did not stop there. At CERN, at Fermilab, at SLSE, ever more sophisticated experiments probed the structure of protons and neutrons. The results converged on a startling truth. Gluons dominate. They do not merely contribute to the proton's structure, they account for most of it. The mass of visible matter in the universe is not due to the quarks themselves, which are almost weightless, but to the binding energy of gluons. The solidity of the world, the weight of your body, the mass of every star is the consequence of invisible glue that cannot be touched, cannot be isolated, cannot be freed. It is an extraordinary irony. The strongest force in nature, the very fabric of reality's weight, comes from something we cannot hold. Consider the scale of this revelation. Every kilogram of matter on Earth, every ton of rock, every star and planet owes its mass not to substance, but to interaction. Gluons, massless themselves, generate mass through confinement energy. The world is heavy not because of particles, but because of forces. Matter is not a thing, but a binding. This overturns every instinct of human perception. We believe in solidity because we feel it. We believe in weight because we carry it. But the universe reveals that solidity and weight are illusions, products of invisible exchanges, consequences of ghosts. Still, doubts linger. Every experiment that points to gluons does so indirectly. We measure the consequences, not the thing. Deep inelastic scattering, 3-jet events, hadron structure functions, all consistent, all persuasive, but none direct. The evidence is overwhelming, yet intangible. Physicists accept gluons as real because nothing else explains the data so well. And yet the possibility remains. What if there is another explanation? What if gluons are a mathematical convenience, an emergent property, an illusion born of patterns too complex for us to disentangle? There are alternative visions. Some propose that the strong force is not mediated by particles at all, but emerges from deeper principles. Others speculate about hidden structures beyond QCD, where gluons are not fundamental but derivative, ripples in a deeper ocean. Such theories remain speculative, but their existence reminds us that evidence, no matter how persuasive, is always provisional. The universe may be preparing to rewrite its own script. For now, though, gluons remain indispensable. Without them, the structure of protons collapses. Without them, deep inelastic scattering makes no sense. Without them, the jets at Petra are inexplicable. Without them, the mass of the universe evaporates. The ghost may not step into the light, but its shadow shapes everything. This raises a profound philosophical question. What does it mean to know something exists if it can only be inferred? We never see a gluon, but we see its fingerprints in every collision, its weight in every star. Is inference enough? Is reality defined by isolation or by necessity? Perhaps gluons force us to abandon the idea that reality must always be tangible. Perhaps reality is broader than our senses, broader than our instruments, broader than our need to touch. And yet, Even as we accept gluons as indispensable, we must face the cost of their intangibility. Physics is a discipline built on observation, on the marriage of theory and experiment. But with gluons, the experiment can never give us the particle itself. We are forever bound to circumstantial evidence, forever denied the direct proof. This is the price of believing in gluons, to accept that the strongest force in nature rests on an article of faith, a ghostly conviction supported by shadows. The tension only deepens as we push to higher energies. At the Large Hadron Collider, proton-proton collisions produce torrents of jets, cascades of particles spraying across detectors. The data screams of gluons, their contributions dominating every interaction. And yet the more we study, the more complex the picture becomes. Gluon distributions inside protons shift with energy, their roles more intricate than first imagined. The ghost grows larger, not smaller, as we probe it. We seize its evidence, but the thing itself slips away. It is tempting to believe that the success of QCD, the overwhelming consistency of the data, proves gluons real beyond doubt. But history reminds us, success is not certainty. Ptolemy's epicycles worked. Newton's gravity worked. Both were surpassed. Perhaps gluons too will one day give way, not disproven, but reinterpreted, reframed, absorbed into a deeper truth. Perhaps the glue of the universe is not particles at all, but something stranger. Strings, fields, vibrations in dimensions beyond our sight. For now, we seize what we can. Scattering patterns, jet distributions, proton masses all whisper the same story. The glue is real. But until we hold it, until we see it, we cannot silence the doubt. We must live in the tension between faith and evidence, between necessity and invisibility, between the ghosts we believe in and the truths we may one day discover. Because in seizing evidence of gluons, we may discover something more profound. That reality itself is not built on things, but on relationships. Not on particles, but on forces. Not on substance, but on shadows that bind. And if that is true, then our entire vision of the universe must change. We have seized the shadows of gluons in experiments, grasped their necessity through theory, and accepted them as the glue of existence. Yet the more tightly we hold, the more they seem to dissolve. And so the doubts begin to surface, not in the controlled confines of mathematics, but in the reality we inhabit. What happens if the very binders of matter are illusions? What would it mean if the glue of the cosmos is only a story we tell ourselves? Consider the proton. Every atom in your body depends upon it. Protons, together with neutrons, form the nuclei around which electrons orbit. They are the anchors of atoms, the bedrock of chemistry. And protons are stable, so stable in fact that a lone proton could, in principle, endure for longer than the current age of the universe. But this stability rests upon confinement, upon the perpetual dance of quarks held together by gluons. If gluons were not real, if the binding force were some deeper illusion, then what guarantee is there that protons are as eternal as we believe? The stability of the visible universe, from the hydrogen in distant galaxies to the iron in your blood, depends upon a ghost we have never seen. Extend this thought further to the stars. In the fiery cores of suns, protons fuse to form helium, releasing the energy that lights the sky. Without gluons, there would be no protons to fuse, no stars, no starlight. The very furnace of creation depends upon the unseen hands of gluons. To doubt them is to doubt the reality of the stars themselves. It is to wonder if the cosmos is a fragile illusion, one breath away from collapse. Of course, we reassure ourselves, the evidence is overwhelming. Protons are stable, stars burn, atoms endure. The gluons must be there, hidden though they are. Yet doubt gnaws. What if our understanding is incomplete? What if the glue is not particles but something deeper, a field we do not yet comprehend, a vibration of strings, an emergent property of space-time itself? What if gluons are not real, but the first approximation of something stranger? This is not idle speculation. Physics has already taught us that reality is not what it seems. Space and time, once thought absolute, are now woven together in relativity. Particles, once thought indivisible, are now probabilities smeared across quantum states. Perhaps gluons, too, belong to this long history of illusions, placeholders for truths not yet revealed. If so, then the foundation of our reality is even more precarious than we imagine. The doubts become sharper when we consider confinement itself. The principle that quarks and gluons can never be isolated is both triumph and tragedy. Triumph, because it explains why matter holds together. Tragedy, because it ensures we can never confirm directly what we most need to know. The very property that makes gluons indispensable also makes them unverifiable. We are left forever at the mercy of inference, of shadows cast on the walls of the quantum cave. Are we, like Plato's prisoners, mistaking shadows for reality? If gluons are shadows, then what of reality itself? The solidity of your chair, the weight of your body, the fire of the stars, all become questions rather than answers. Reality would not be what it seems, but a performance, a theater of appearances stitched together by illusions at the smallest scales. What does it mean to live in a world where the glue that binds existence is itself uncertain? The philosophical implications are unsettling. We want the universe to be firm, to be knowable, to be real. But perhaps reality is not firm at all. Perhaps it is fragile, contingent, provisional. Perhaps what we call solidity is merely a temporary arrangement of shadows. Gluons, in their elusiveness, force us to confront this possibility. They force us to accept that the ground beneath our feet may not be ground at all, but quicksand, stable enough for now, but shifting in ways we cannot predict. There are practical consequences too. If gluons are not real in the way we imagine, then our models of the universe may be flawed. Predictions of proton stability, of stellar fusion, of nuclear processes could be built on sand. Perhaps this is why some experiments hint at anomalies, why some theories reach beyond QCD towards string theory or holography. Perhaps we are already seeing cracks in the illusion, and yet even in doubt, there is awe. The fact that the stability of the cosmos depends upon invisible entities we can never isolate is extraordinary. The fact that your very existence depends upon ghosts is a reminder of the strangeness of reality. Even if gluons are not real in the ordinary sense, their effects are undeniable. The stars burn, atoms endure, life exists. The shadows may be illusions, but the play they produce is no less profound. This duality between certainty and doubt, between shadow and substance, is at the heart of the human experience of science. We search for truth, but truth slips away. We demand reality, but reality dissolves. Gluons embody this paradox. They are the glue of matter, and yet they may not exist as we imagine. They hold the world together, and yet they leave us questioning the world itself. It is tempting to dismiss these doubts, to cling to the evidence and declare the case closed. But science advances by doubt, not by certainty. To question gluons is not to abandon them, but to prepare for the possibility of deeper truths. Perhaps the glue of the universe is not particles at all, but geometry, topology, or vibrations of hidden dimensions. Perhaps the gluons are not illusions, but approximations of a reality beyond our imagination. And so we live in the tension. We believe in gluons because without them the universe collapses, but we doubt them because they can never be isolated, never confirmed. We are suspended between necessity and uncertainty, between evidence and illusion. And in that suspension, reality itself begins to tremble. Because if gluons are shadows, then everything we see, from the atoms in your hand to the fire of the stars, may be nothing more than the echo of a truth we have yet to glimpse. Every path we take in the search for gluons leads us to a single, inescapable wall: confinement. It is not merely an experimental limitation, not merely a technical obstacle. It is a fundamental law of the strong force. Quarks and gluons are bound forever. No amount of energy, no collider however vast, no clever detector can ever extract them as free particles. They are condemned to remain imprisoned within protons, neutrons, and other hadrons. And this is the crisis at the heart of the gluon. How can something be real if it can never be seen outside of its cage? To grasp the depth of this crisis, we must look closely at the strange mechanics of confinement. Unlike the electromagnetic force, which diminishes with distance, the strong force grows stronger the farther quarks are pulled apart. It is like a rubber band that stretches tighter and tighter, resisting separation with increasing fury. The more energy you pour into trying to rip quarks apart, the stronger the force becomes. Eventually, the energy becomes so great that the vacuum itself responds. A new quark-antiquark pair is created, snapping into existence to neutralize the attempt. The original quarks remain bound, but now accompanied by new companions, each locked in its own prison. The walls of confinement do not break, they multiply. This is why we never observe free quarks or free gluons. Every attempt to liberate them produces only new hadrons, new prisons, new confinements. It is a law of nature, merciless and absolute. The crisis is not that we lack the technology, but that the universe itself forbids us from success. For gluons, the situation is even more severe. They are carriers of the strong force, but unlike photons of light, they themselves carry the very charge they mediate. Photons glide past one another without interaction. Gluons snarl, twist and bind with one another, locked in a web of self-interaction. This self-binding is what makes confinement possible, but it also ensures their invisibility. A gluon cannot exist alone because it is chained to every other gluon in a seething, inseparable network. Reality allows us to describe them, but never to free them. This paradox cuts to the heart of our idea of what it means to exist. A chair exists because you can sit on it. An electron exists because you can trap it in a magnetic field and measure its charge. A photon exists because it can trigger a detector, leaving an unmistakable signal. But a gluon, it cannot be trapped, cannot be isolated, cannot leave a direct mark. Its only trace is in the jets of particles that explode from collisions, indirect echoes of an event we cannot see. If existence is defined by observation, then gluons defy existence. Yet if existence is defined by necessity, they are indispensable. This is the crisis of confinement. To believe in gluons is to accept a reality that can never be verified in the way we are accustomed. It is to abandon the comfort of direct observation and live in the shadows of inference. It is to accept that some truths, however central, may never be touched. The philosophical consequences are profound. Science has always thrived on verification, on the marriage of theory and experiment. But confinement forces us to question whether this marriage is always possible. Can we truly know something if we can never observe it directly? Can we build an edifice of science on entities that live only in equations, never in isolation? Or must we rethink what it means for something to be real in the first place? Some physicists argue that gluons are not particles in the conventional sense at all, but excitations of fields. Just as the electromagnetic field gives rise to photons, the color field gives rise to gluons. But unlike photons, these excitations cannot travel free. They are bound forever to the field itself. If this is true, then perhaps our error is in thinking of gluons as particles at all. Perhaps they are not discrete objects, but ripples in a field so tightly woven that it never unravels. Others turn to string theory, where gluons emerge not as fundamental particles, but as vibrations of tiny strings. In this framework, confinement arises naturally. The strings that represent gluons cannot break without spawning new ones. The crisis of confinement becomes a clue to a deeper reality, where what we call gluons are only shadows of vibrating geometries in hidden dimensions. If so, then gluons are not phantoms, but the visible edge of something vastly more intricate. But even if these interpretations are correct, the crisis remains. We are left with entities we cannot isolate, truths we cannot confirm directly. We are forced to trust in mathematics, in indirect evidence, in the coherence of theory. The gluon becomes not only the glue of matter, but the glue of our own faith in science. And that faith, fragile as it is, becomes essential. Consider the irony once more. The strongest force in nature is also the most elusive. The glue that holds the universe together is also the most intangible. The entities most necessary for reality are also those most denied to our senses. This is not merely a scientific challenge, it is an existential riddle. What kind of universe binds itself with ghosts? The crisis of confinement also touches on human notions of freedom. In our world, to be free is to be unbound, unshackled, to exist independently. But in the quantum realm, freedom is impossible. Quarks and gluons can never exist alone. Their very nature is to be confined, to exist only in relation to others. They are defined not by individuality, but by binding. Perhaps this is the deepest lesson of confinement, that reality itself is relational, that nothing exists alone. Every particle, every force, every aspect of matter is entangled in webs it can never escape. And so, the crisis of confinement is not only a challenge to physics, but to philosophy. It demands that we abandon the dream of isolated reality and embrace a universe where existence is always shared, always bound, always dependent. The gluon, in its eternal imprisonment, forces us to confront this truth. Yet questions linger. If confinement is absolute, why do we sometimes glimpse hints of quark-gluon plasma, fleeting states where quarks and gluons appear liberated? If gluons are forever bound, what does it mean that their collective behavior shapes entire states of matter? Is confinement absolute, or is it itself an illusion, a property that breaks down under conditions we have only begun to explore? This uncertainty sharpens the crisis. We are trapped between absolutes and anomalies, between the conviction that confinement is eternal and the suspicion that it might not be. Perhaps the walls of confinement are not solid, but porous. Perhaps the gluon's prison is not impenetrable, but conditional. And if so, then our entire understanding of the strong force may one day collapse into a deeper theory. For now, we live with the crisis. We believe in gluons because we must. We accept confinement because it explains the world. But beneath this acceptance lies doubt, and beneath doubt, awe. We stand at the edge of knowledge, staring into a prison we cannot breach, knowing that within it lies the glue of reality itself. Because if confinement is real, then the universe is built not on freedom, but on eternal captivity. And if confinement is an illusion, then everything we know about matter is waiting to be undone. After so much doubt, after so many ghosts and prisons, the story of gluons offers a moment of triumph. For if confinement is an ordeal, then quantum chromodynamics is the reward. A theory so precise, so predictive, that it illuminates the strong force with a clarity once thought impossible. In its grasp, gluons are not illusions, but indispensable actors in the greatest stage of nature. The reward of the hunt is not the capture of the ghost, but the realization that even phantoms can shape reality with unyielding authority. To appreciate this triumph, consider the scope of what QCD has achieved. Before its development, the subatomic world was chaos, an endless zoo of particles, each seemingly unrelated to the next. Mesons, baryons, resonances, they emerged in experiments like strange beasts from a dark sea, overwhelming any attempt at order. But with QCD, a pattern emerged. All these particles could be understood as bound states of quarks and gluons, their properties predicted by the dynamics of the strong force. The chaos became order. The zoo became a system. This predictive power was not abstract. QCD explained the mass differences among hadrons, the decay patterns of particles, the scattering results from accelerators. It predicted asymptotic freedom, quarks behaving as though nearly free at high energies, long before experiments confirmed it. It accounted for the strange stability of protons and neutrons, for the binding of nuclei, for the consistency of the atomic world. Each success was a vindication. Each success pulled gluons closer from shadow into substance. Nowhere is this reward clearer than in the structure of matter itself. Quarks are nearly massless, their combined weight accounting for less than 1% of the proton. The rest, the other 99% of your body, of Earth, of every star, arises from gluons, from the seething storm of their binding energy. Imagine the paradox, particles with no mass creating nearly all mass in the universe. It is an achievement of QCD to show how this is possible. Without gluons, we would weigh almost nothing. With them, the universe becomes heavy, substantial, real. If there is a reward for the crisis of confinement, it is this: understanding that the glue we cannot see is the true source of existence. Experiments have borne out these predictions with startling precision. At the Large Hadron Collider, detectors record jets of particles that can only be explained by gluon dynamics. At RHIC, collisions of gold ions produce quark-gluon plasma, whose behavior matches QCD calculations. In deep inelastic scattering, the structure functions of protons reveal gluon distributions that dominate over quarks. Everywhere we look, the data insists. Gluons are there, shaping reality, unseen but undeniable. There is triumph, too, in the elegance of gluon jets. When protons collide at high energies, gluons often emerge as sprays of particles fanning outward. Detectors record these showers in beautiful patterns, precise in their geometry, predictable in their spread. These jets are the fingerprints of gluons, delicate yet powerful. To see them is to glimpse the invisible, to know that the equations of QCD have captured something real. They are the closest we may ever come to seeing a gluon, and their existence is a victory for theory, a reward for faith. Yet the reward is not only scientific. There is a philosophical triumph in realizing that the world is bound by forces beyond sight, that reality is held together by invisible hands. To live in a universe where the strongest force is unseen is to confront the limits of human perception and to transcend them. Gluons remind us that reality is not constrained by our senses. It is deeper, stranger, more intricate. The reward of the hunt is not only the data, but the humility it inspires. But the reward is not complete. For even in triumph, shadows linger. QCD, for all its power, is incomplete. Calculations at low energies remain intractable, requiring lattice simulations and approximations. The theory explains confinement but cannot derive it analytically, and beyond the standard model, mysteries remain: dark matter, dark energy, unification with gravity. Gluons explain the weight of the visible universe, but they cannot account for the unseen mass that dominates the cosmos. The reward, though immense, is partial. Still, the triumph matters. Without gluons, the world would be formless. Without QCD, the chaos of the particle zoo would remain unexplained. Without the ghostly glue, the stars themselves would not shine. To doubt gluons is to doubt everything, but to accept them is to see the universe illuminated with new clarity. This is the paradox of the reward. It is not proof, but it is power. It is not direct evidence, but it is understanding. There is also a poetic symmetry in the role of gluons. Ancient myths spoke of forces that held the cosmos together: the world tree, the cosmic serpent, the bonds of divine order. In QCD, we find a scientific equivalent. Gluons are the binders, the invisible hands, the threads that weave reality. They are the scientific heirs of myth, their elegance replacing mythic imagery with mathematics. To embrace them is to see science not as a dry catalogue, but as a continuation of humanity's oldest quest to understand what holds the world together. The reward, then, is twofold. In science, we gain predictive power, precision, the ability to describe and control. In philosophy, we gain perspective, awe, and humility before forces unseen. Gluons, though ghosts, are the glue of both matter and meaning. They remind us that reality is larger than our senses, that truth is larger than direct proof, that the world is bound by mysteries we can only glimpse. And yet, the story cannot end in triumph. For every reward in science opens new questions. If gluons generate nearly all mass, why do we still speak of particles as if they are things, rather than patterns of force? If gluons are massless, how do they create weight? If gluons cannot be isolated, can they be said to exist at all? The reward is not the resolution of doubt, but the deepening of it. Gluons illuminate the strong force, but in their light we see new shadows. So we pause here at the height of the journey to acknowledge what has been won. The standard model stands triumphant. QCD explains the zoo of particles. Gluons, though unseen, are everywhere in evidence. The reward has been seized: illumination, clarity, understanding. But as the path winds forward, resistance returns. The deeper we travel, the more the triumph fades into questions. For the reward is not the end, it is only the midpoint. Beyond it lies the road back, where ancient philosophies and modern doubts converge. Because if the gluons are real, then they bind the universe. But if they are not, then the universe itself may be bound by illusions we have yet to name. The road back from triumph is rarely smooth. After illumination comes reflection, and reflection often reveals shadows. For while quantum chromodynamics has given us a framework to understand gluons, the question of their reality persists. And strangely, as we look forward into the frontiers of physics, we also find ourselves looking back to the earliest philosophies of matter, when thinkers first imagined the universe not as chaos, but as order woven by unseen bonds. 2.5 millennia ago, Democritus and Leucippus proposed that all matter was made of indivisible units called atoms. To them, atoms were eternal, uncuttable, the bedrock of reality. Everything we see, stars, stones, human beings, was the product of these tiny seeds moving in the void. Their philosophy was radical, stripping the cosmos of gods and magic, leaving only particles and emptiness. But even they knew the atoms could not bind themselves alone. Something had to explain their cohesion, their motions, their structures. They imagined eternal laws, but those laws remained mysterious. Now, 25 centuries later, we find ourselves echoing their struggles. We have gone deeper than atoms, deeper than protons and neutrons, into quarks and gluons. And what do we find? The same paradox. Entities that exist only in confinement, bound by unseen forces, we can describe but never isolate. Where Democritus spoke of atoms, we speak of quarks. Where he invoked eternal motion in the void, we invoke gluons, weaving bonds of color charge. The names have changed, the mathematics has deepened, but the mystery remains. We are still trying to explain why matter holds together, still searching for the glue of existence. The ancients spoke in metaphors. They imagined atoms as miniature stones, indivisible seeds, tangible in principle if not in practice. They imagined void as the space in which those seeds moved. But we now know that atoms are not indivisible, that protons are not eternal beads, that gluons cannot be touched at all. Our metaphors are equations, our visions are simulations, but the distance from ancient thought may not be as great as we believe. For in both cases, the core question is the same. How can there be unity in a universe of fragments? In modern physics, gluons provide one answer. They form flux tubes, invisible strings of force that stretch between quarks. These flux tubes grow tighter as quarks are pulled apart, binding them inescapably together. To visualize them is to imagine invisible ropes woven of pure interaction, ropes that can never be cut. It is an image that would not have been foreign to ancient thinkers. They too imagined bonds, though they gave them names like love and strife or cosmic order. Where Empedocles spoke of forces binding the four elements, we speak of color charge and gluon exchange. The forms change, but the themes endure. The parallels raise unsettling questions. Are we uncovering truths the ancients intuited, or are we dressing old myths in new language? When we speak of gluons as the glue of matter, are we describing reality, or are we echoing metaphors older than science itself? Perhaps our belief in unseen binders is not purely empirical, but deeply human, a reflection of our need to impose unity upon fragmentation. Perhaps gluons are not only particles of theory, but archetypes of thought. This does not mean they are illusions. The predictions of QCD are precise, the evidence persuasive, but it does mean we should be cautious. The road back from triumph passes through a landscape littered with ghosts of past certainty. The ether was once indispensable, phlogiston once necessary. Now they are gone, remembered only as cautionary tales. The ancients believed in atoms as solid beads, but we now know atoms are mostly void. Our certainty may one day share the same fate. And yet there is something profound in the continuity. The idea that matter is bound by invisible forces has survived across millennia, transformed but never destroyed. Perhaps this persistence suggests a deeper truth, that the universe really is bound by threads we cannot see, whether we call them flux tubes, strings, or something else. Perhaps the shadows of antiquity are not merely errors, but echoes of intuition, glimpses of truths that mathematics would one day sharpen. In this light, gluons become more than particles of theory. They become symbols of humanity's quest to understand cohesion. Why does the world not fall apart? Why does matter persist? Why is there order in the void? These questions haunted Democritus as much as they haunt us. Gluons are our modern answer, but the questions are eternal. The road back is also a road of resistance. Not everyone accepts gluons as final truth. Some see them as temporary scaffolds, destined to be replaced by deeper theories. Perhaps gluons are emergent phenomena, not fundamental at all. Perhaps they are the visible traces of hidden dimensions, or the collective behavior of a deeper field. If so, then our belief in gluons may be akin to the ancients' belief in indivisible atoms, a step along the way but not the destination. This tension between past and present forces us to confront our assumptions. Are we uncovering the universe or projecting our own patterns onto it? Do we believe in gluons because they are real or because we need them to be? The road back demands that we face these questions honestly. For if we mistake metaphors for truths, we may once again be clinging to shadows. And yet, even as doubts rise, there is beauty in the continuity of human thought. From ancient Greece to modern CERN, we have always sought the same thing: to understand why the universe holds together. Gluons are our answer for now. They bind not only quarks but also our intellectual lineage, tying us to thinkers long gone. The road back reminds us that science is not a break with the past but a continuation of it. Our ghosts are ancient, and they still walk with us. So as we leave the triumph of QCD and step into reflection, we carry both light and shadow. We have illuminated the strong force, but we see echoes of myths behind our equations. We have given gluons mathematical precision, but we sense their metaphorical weight. The road back is not only scientific but philosophical, a reminder that every theory is both discovery and story, both truth and metaphor. Because if ancient intuition still lingers in our most modern equations, then perhaps the universe has always been whispering the same truth: that reality is bound by unseen threads, and that to seek them is to chase shadows through time. For decades, gluons lived at the edge of belief, indispensable in theory, persuasive in experiment, yet forever hidden by confinement. but the human pursuit of truth rarely accepts impossibility. If gluons cannot be seen directly, then perhaps they can be resurrected in another form, through simulation. And so physicists turn to one of the most unlikely tools for probing reality, the computer. From this union was born lattice quantum chromodynamics, a method by which gluons, though forever confined in the physical world, can be coaxed into visibility in a virtual one. At its core, QCD is a theory of infinite complexity. The equations that describe quarks and gluons are nonlinear, tangled webs of self-interaction. At high energies, the math simplifies. Quarks behave as if free, gluons' grip loosens, and perturbative calculations become possible. But at low energies, the realm of confinement, the very place where the nature of gluons is most crucial, the equations spiral into chaos. No analytic solution exists. The math collapses into infinities. To see gluons at work where they matter most, physicists needed a new strategy. Lattice QCD was that strategy. Conceived in the 1970s, it transforms continuous spacetime into a discrete grid, a lattice of points through which quarks move and gluons bind. On this grid, the impossible becomes calculable. The interactions of gluons, their flux tubes, their confinement, can be modeled step by step, probability by probability, across billions of computational iterations. In this artificial universe, gluons leave fingerprints more direct than any collider can reveal. The results were staggering. Lattice simulations showed that gluons form flux tubes, thin strings of force stretching between quarks. As the quarks are pulled apart, the flux tube does not weaken but grows tighter, confirming the mechanism of confinement. Eventually the tube snaps, not by breaking, but by spawning a new quark-antiquark pair, sealing the prison anew. The ghost of the gluon, long invisible in experiment, now danced vividly across supercomputer screens. This was resurrection. Not resurrection in the sense of freeing gluons into the world, but in reviving their reality in a space where they could be visualized, studied, even measured. The gluon became not merely an inference, but a presence tangible in computation. Its behavior, its interactions, its role in binding matter, all could be mapped with precision. From these simulations came another triumph, the calculation of hadron masses from first principles. For the first time, physicists could compute the masses of protons, neutrons, and other particles directly from QCD. The results matched experiment with astonishing accuracy. The mass of the visible universe, it turned out, could be derived not from assumption, but from the dance of quarks and gluons on a lattice grid. This was not mere theory, it was confirmation. The ghost had left measurable footprints. And yet, even in resurrection, ambiguity lingers. Lattice QCD is not the universe itself, but a model of it. It requires approximations, finite grids, enormous computational power. The gluons that appear on a lattice are not particles observed in nature, but mathematical constructs. Are they real in the same sense as electrons, which can be trapped and counted? Or are they real only in the sense that simulations are real, precise representations of patterns that we cannot otherwise touch? The resurrection raises the same question it sought to resolve. Does proof in virtual space confirm reality in physical space? Still, the achievement is undeniable. Lattice QCD has given physicists the ability to explore gluons in ways experiments cannot. It has revealed the structure of flux tubes, the energy distributions inside hadrons, the behavior of quark-gluon plasma under extreme conditions. It has turned shadows into shapes, ghosts into data. Without it, our knowledge of gluons would remain an abstraction. With it, the gluon stands revived, not as a free particle, but as a calculable reality. There is also something poetic in this resurrection. Gluons, forever confined in the physical universe, find freedom in a virtual one. They cannot exist alone in nature, but they can in mathematics. They cannot be seen by the eye, but they can by the algorithm. In this sense, lattice QCD is more than a tool. It is a metaphor for human ingenuity. Where reality denies us access, we build new realities. Where the universe withholds its truths, we create mirrors in which those truths reveal themselves. But resurrection is not certainty. Even lattice QCD cannot silence the doubts. The calculations are immense, stretching supercomputers to their limits. The approximations may conceal as much as they reveal. The results, though consistent, may yet be incomplete. The gluon lives in computation, but does it live in nature? Or are we once again chasing shadows, this time in digital form? Philosophers of science might argue that this is enough. Reality is what predicts, what explains, what holds together our experience of the world. By this measure, gluons are real, resurrected not in isolation but in their power to account for what we see. They need not be free particles to be real. Their confinement is not a weakness but a property. In this view, the resurrection is complete. Gluons are real because nothing else explains the universe so well. And yet, the unease remains. For what if there is a deeper theory beneath QCD, one that renders gluons obsolete, just as phlogiston and ether once were? What if the lattice is showing us not the final truth, but the scaffolding of a greater one? What if gluons are not particles at all, but emergent properties of a deeper field or geometry? In resurrecting them, are we confirming their reality or preserving an illusion? This is the paradox of resurrection. To revive gluons through lattice QCD is to give them presence, to pull them from ghostliness into data. But to do so is also to risk mistaking model for reality, calculation for truth. The gluon lives again, but whether it lives in the universe or only in our equations remains the haunting question. Still, the resurrection is a triumph. It has given us tools to predict, to calculate, to understand. It has turned shadows into measurable patterns. It has shown us that the strongest force in nature can be illuminated, even if only virtually. And in doing so, it has reshaped our conception of reality itself. For if the glue of the universe can be resurrected in computation, then perhaps reality is not what we touch, but what we calculate. Perhaps truth is not isolation, but coherence. Because in the end, the resurrection of the gluon is not only about physics. It is about the human capacity to wrest meaning from the inaccessible, to revive ghosts with mathematics, to find reality in places where the senses cannot go. The gluon may never be freed in the world, but in the lattice it lives. And if that is enough, then the glue of the universe has been found. Every great journey returns with an elixir, not always the treasure expected, but a transformation that changes how the world is seen. For the seeker of gluons, the elixir is not certainty, but doubt. It is the realization that the very glue of the universe, the force that binds quarks into protons and protons into stars, may never be isolated, never confirmed in the way we once demanded. And yet, in that doubt, there is wisdom. The path has been long. We began with the illusion of atoms as solid beads, then plunged into the abyss of quarks and gluons, where reality frayed. We pursued the ghost through colliders, theories, and simulations. Each step gave us evidence, clarity, predictive power, and yet the gluon itself remained intangible, forever chained by confinement. What we have gained is not possession, but perspective. Not certainty, but humility. This is the elixir of quantum doubt. At first, such doubt feels like failure. Science seeks truth, clarity, confirmation. To admit that we cannot free a gluon, cannot see it directly, seems a defeat. But look closer. Doubt is not the absence of knowledge, it is its refinement. It forces us to abandon illusions, to question assumptions, to remain open to deeper truths. In this sense, the gluon teaches us that reality is not about certainty, but about persistence in the face of mystery. Consider what this doubt reveals. We once believed the atom indivisible. We once believed space and time absolute.
We once believed light required ether. Each of these certainties was overturned, not by denying reality, but by doubting our assumptions. The gluon continues this lineage. It reminds us that what we take as real may be provisional, that our theories may be scaffolds awaiting replacement. To live with doubt is to remain alive to discovery.
The elixir of quantum doubt also reshapes our view of reality. If gluons are real only in confinement, only as relationships, then perhaps reality itself is not built of isolated things, but of patterns, interactions, and connections. Existence may not be substance, but relation. Doubt dissolves the illusion of solidity and reveals a universe woven of bonds, not bricks. This is not a weakness, but a deeper truth. It shows us that the world is more intricate, more relational, more fragile than we imagined. And what of the universe beyond? If gluons are shadows we can never hold, what does that say of dark matter, dark energy, gravity itself? These forces too are ghosts, inferred but unseen. The elixir of doubt prepares us to face them honestly, without clinging to illusions of certainty. It reminds us that science is not about final answers, but about ever-deepening questions. The gift is not closure, but openness. This doubt also humbles us. We are creatures who crave solidity, who want to touch and hold. Yet the universe denies us this comfort. It gives us shadows, patterns, ghosts, and still it sustains us. Stars burn, atoms endure, life flourishes, all held together by forces we cannot see. Doubt teaches us to live without possession, to accept that reality may always exceed our grasp. It is a difficult lesson, but a liberating one. There is even beauty in this uncertainty. The fact that the strongest force in nature rests upon ghosts is not a flaw, but a wonder. It shows us that reality is not simple, not mechanical, but layered with paradox. Gluons, forever confined yet indispensable, embody the mystery of existence itself. They remind us that truth may be unreachable, but meaning lies in the pursuit. The elixir of doubt is not despair, but awe, and it is an elixir we can carry into every domain. In philosophy, it reminds us that certainty is illusion, that knowledge is provisional, that humility is wisdom. In science, it drives us to seek deeper theories, to question the foundations, to never rest content with partial answers. In life, it teaches us that relationships, not substances, are the heart of reality. Just as gluons exist only in their binding, so do we, defined not in isolation, but in connection to others. This is perhaps the most profound gift of the gluon's ghost, the recognition that existence itself may be relational. Nothing exists alone. Quarks do not exist without gluons. Stars do not exist without quarks. We do not exist without stars. The elixir of doubt shows us the chain of being not as a hierarchy of things, but as a web of relationships. It is a vision both humbling and unifying. Of course, doubt does not end the story, it only deepens it. Perhaps new theories will arise, string theory, holography, some future framework that reveal gluons as emergent illusions, shadows of a deeper reality. Or perhaps gluons will endure, forever unfree but forever indispensable. Either way, the lesson of doubt will remain, that certainty is dangerous, that humility is essential, that the search never ends. And so we return with the elixir. We began in comfort, in the illusion of atoms as solid and certain. We descended into chaos, pursued ghosts through fire and theory, endured the crisis of confinement. We emerged with illumination, only to find ourselves face to face with the shadows of antiquity. And now we return, transformed, not with certainty, but with doubt. Not with possession, but with humility. The gift is not the gluon itself, but the perspective it forces upon us. Because in the end, the gluon teaches us a truth larger than itself. That reality is never simple. That certainty is never final. That the strongest forces are often unseen, the most important truths forever beyond touch.
The elixir of quantum doubt is not weakness, but wisdom. The wisdom to live in a universe of ghosts and to find meaning in the chase.
And as we carry this elixir home, one question lingers, haunting and inexhaustible. If the glue of existence is invisible, intangible, confined forever beyond our reach, then what other ghosts bind the universe, waiting to be named? Every scientific triumph carries with it new trials. Success breeds scrutiny, and clarity invites challenge. Gluons, despite their centrality in quantum chromodynamics, are no exception. For all their necessity, for all the elegance of the theory that enshrines them, there remain alternative visions of reality, interpretations that question whether gluons are truly what we think they are. The journey into the heart of matter does not end with their acceptance. It forks into battles of interpretation where each rival theory contends for the soul of the strong force. One of the earliest rivals emerged in the 1970s at the very birth of QCD itself. While quarks and gluons provided a compelling framework, some physicists doubted their reality. Instead, they proposed technicolor theories, models in which the strong force is not mediated by gluons at all, but by entirely different particles bound by new interactions. In these visions, what we interpret as gluons are emergent effects, illusions produced by deeper layers of physics. Technicolor fell out of favor as experiments confirmed the predictions of QCD with increasing accuracy, but the very fact of its existence is telling. From the beginning, not everyone was convinced that gluons were the answer. Other alternatives have lingered in the margins. Some theorists argue that gluons are not fundamental but emergent phenomena. Just as sound waves are not fundamental particles but collective vibrations of atoms, perhaps gluons are collective excitations of a deeper field. In this view, the mathematics of QCD is not wrong, but incomplete, a macroscopic description of something finer. The strong force in this vision might not be carried by particles at all, but by structures we cannot yet imagine. Still others turn to holographic theories of the universe, where space-time itself is a projection of information encoded on distant boundaries. In such models, gluons may be nothing more than the shadows of deeper geometrical truths. Their confinement may be a reflection not of particle behavior, but of the way information is stitched into the fabric of reality. If this is true, then gluons are not particles in the universe, but echoes of mathematics beyond it. Each of these interpretations carries risks. They may be elegant, but elegance alone cannot withstand experiment. QCD, with its predictive precision, continues to dominate because it works. Every scattering experiment, every jet distribution, every lattice simulation confirms its power. Yet cracks in interpretation persist. Gluons may be indispensable, but their nature is not beyond dispute. Are they particles, fields, vibrations, or illusions? The trials of interpretation are not only scientific, but philosophical. What does it mean for something to be real if its only evidence is indirect? Is inference enough? If gluons are necessary in theory but forever hidden in practice, do they belong in the same category as electrons, which can be isolated, or photons, which can be counted? Or are they something different, theoretical entities whose reality is defined by their necessity, not their presence? These questions haunt the philosophy of science. Karl Popper argued that scientific theories must be falsifiable, capable of being tested. But can gluons ever be falsified, given confinement? We can falsify QCD perhaps if its predictions fail, but the gluon itself, forever invisible, may never be directly tested. Does this make it less real, or does its indispensability outweigh the lack of direct evidence? The trials of interpretation are as much about epistemology as about physics. There are also deeper tensions within QCD itself. At high energies, where perturbative calculations work, gluons behave like ordinary particles, their effects calculable and precise. But at low energies, where confinement dominates, the equations collapse into intractability. We rely on lattice simulations, approximations, numerical tricks. Does this mean gluons are real only in one regime and emergent in another? Or does it mean our understanding of them is fundamentally incomplete? The experimental data itself sometimes stirs doubt. While gluon jets are consistent with theory, they are still indirect. Proton structure functions reveal gluon distributions, but only through complex interpretations. Quark-gluon plasma behaves as predicted, but in ways that raise further questions. Each triumph is shadowed by uncertainty. Each success conceals new ambiguity. The trials of interpretation multiply, not diminish, as our knowledge deepens. And beyond physics, there is metaphor. Gluons have become symbols of unseen forces, metaphors for cohesion, for the invisible bonds that hold the world together. This dual role, scientific and symbolic, complicates their interpretation. Are we seduced by the metaphor as much as by the math? Do we believe in gluons because they are real, or because the idea of a cosmic glue satisfies a human longing for order? The trials of interpretation are not only about data, but about desire. The danger is clear. History warns us of phlogiston, ether, caloric, entities once indispensable, now discarded. They too explained data, too seemed necessary, too satisfied the hunger for cohesion. But they were illusions, replaced by deeper truths. Could gluons share their fate? Could QCD, for all its triumph, one day be revealed as scaffolding, not bedrock? The trials remind us to be cautious, to never confuse necessity with finality. Yet there is also resilience. Unlike ether or phlogiston, QCD has withstood decades of precision tests. Its predictions align with experiment to extraordinary degrees. It explains phenomena that nothing else can. Gluons may never be freed, but their fingerprints are everywhere. If they are illusions so effective that reality itself obeys them. And perhaps that is the ultimate measure of reality. Not isolation, but influence. Not freedom, but indispensability. In the end, the trials of interpretation are not a weakness, but a strength. They keep us vigilant, remind us that science is provisional, that certainty is dangerous. They ensure that gluons remain not dogma, but question. They keep the search alive, the door open to deeper truths. And so, the journey enters its final stages. We have seized the reward of QCD, returned with the elixir of doubt, endured the trials of interpretation. Ahead lies the ultimate boon, not certainty, but cohesion. For in gluons, whether real or ghostly, we glimpse not only the binding of matter, but the binding of meaning itself. Because if the universe is held together by unseen threads, then perhaps so too is our understanding. And perhaps the ultimate truth of the gluon is not whether it is real, but what it reveals, that reality itself is woven of forces we can never hold, but without which nothing would exist. Every mythic journey promises a final boon, not always treasure, but revelation. In the story of gluons, the boon is not the capture of an elusive particle, but the recognition of what gluons symbolize. They embody cohesion itself, the hidden bonds that hold the universe together, the unseen unity beneath fragmentation. Whether real in the tangible sense or real in the relational one, gluons stand as symbols of the deeper truth that reality is not made of isolated things, but of connections. The scientific triumph of QCD already demonstrated their indispensability. Without gluons, quarks would drift apart, protons would dissolve, stars would never ignite. 99% of the mass of the visible universe arises not from particles, but from gluonic energy. The world is not built on substance, but on binding. That is the scientific boon, understanding that reality's solidity emerges from ghosts we cannot isolate. But beyond science, the gluon becomes a symbol of philosophical cohesion, of the universal threads that weave cosmos, thought, and even human life together. Consider the cosmic scale. Astronomers map the large-scale structure of the universe, the cosmic web of galaxies stretched across billions of light years. Vast filaments of matter thread through the void, clustering into nodes where galaxies collide. It is an image hauntingly similar to gluon flux tubes, the invisible strings binding quarks together. At the smallest and largest scales, the same metaphor appears: webs, threads, connections. The universe is not random chaos, but structure woven by unseen bonds. Gluons in their confinement are a microcosm of the cosmos, threads that never break, cohesion without freedom. This symmetry extends into philosophy. The human mind has long wrestled with the problem of the one and the many, how unity arises from multiplicity. Plato spoke of forms, Aristotle of substance, Spinoza of substance monism, Hegel of synthesis. Each sought to explain how diversity could be reconciled with unity. Gluons provide a physical analog. They show how individuality is impossible without relationship, how quarks cannot exist alone, how matter is unity forged from multiplicity. The philosophical boon is the realization that existence itself may be nothing more than binding, that the very idea of thingness is secondary to relationship. The boon extends further still into the human domain. For just as quarks cannot exist without gluons, humans cannot exist without bonds. We are defined not in isolation, but in connection. Families, communities, histories, cultures. Our very identity is relational. To see gluons as metaphors of cohesion is to recognize that human meaning, like physical reality, arises not from solitary atoms, but from the threads that weave them together. The physics of the strong force becomes a mirror of the human condition. This philosophical cohesion is not sentimental but sobering. The gluon reminds us that freedom in the quantum realm does not exist. Quarks are forever confined, gluons forever bound. Their reality is imprisonment, and yet from that imprisonment arises the richness of the universe. This is a profound inversion of human values. We equate freedom with possibility, confinement with limitation. Yet in the cosmos, confinement is creation. Without it, there would be no matter, no stars, no life. Cohesion is not the enemy of freedom, but its foundation. The boon of the gluon is to teach us that what appears as limitation may be the source of all possibility. And yet, there is danger in this realization. To universalize cohesion is to risk romanticizing it, to forget the destructive forces of false unity, dogma, tyranny, the suppression of individuality. The gluon must be understood carefully. Cohesion is necessary, but so is tension. Quarks are bound, but they remain distinct. Gluons confine, but they also allow motion within confinement. The lesson is not that individuality should vanish into unity, but that individuality without cohesion collapses into nothingness. It is a balance, delicate and eternal. From this perspective, the philosophical boon is clear. The gluon teaches us that reality is not built on isolated things, but on webs of connection. That cohesion, not independence, is the foundation of existence. That unity and multiplicity are not opposites, but interdependent. It is a lesson as scientific as it is existential. Still, shadows linger. Even in the boon, doubt persists. Gluons may be indispensable, but are they fundamental? Are they the bedrock of reality, or are they scaffolds hiding a deeper truth? Perhaps string theory is correct and gluons are vibrations of deeper geometries. Perhaps holography is true and gluons are projections of information written on cosmic boundaries. Perhaps there are layers of cohesion beneath cohesion, forces beneath the strong force. The boon does not resolve the mystery, it deepens it. Cohesion is real, but its source may forever escape us. And so, the ultimate boon is not certainty but perspective. It is the recognition that the universe is held together by unseen forces, that reality is relational, that existence is binding. It is the humility to accept that our truths may be provisional, our metaphors fragile, our theories temporary. It is the awe of realizing that the strongest force in nature rests upon ghosts we can never see. There is even a kind of poetry in this. Human beings have always imagined the world as threads, the fates weaving destinies, the world tree binding realms, Indra's net stretching infinite jewels. Gluons are the scientific counterpart of these myths, threads not of story, but of mathematics. They are the modern incarnation of an ancient intuition that reality is woven, not built, connected, not isolated. The boon of the gluon is to see science and myth not as opposites, but as parallel expressions of the same longing to understand what holds the world together. And so, the journey nears its end. We began with the illusion of solidity, descended into the abyss of quarks, hunted ghosts, endured confinement, seized illumination, carried doubt, and faced rival interpretations. Now we arrive at cohesion, the boon that unifies science and philosophy. The gluon may remain elusive, but its lesson is clear. The universe is held together by unseen bonds, and to exist is to be bound. The question that lingers is not whether gluons are real, but what their reality means. If they are ghosts strong enough to hold stars. If they are illusions that create mass. If they are real in ways that defy our categories. The boon is not an answer, but a transformation, a new way of seeing the world, one where cohesion is primary and isolation is an illusion. Because in the end, the ultimate boon of the gluon is not that it proves itself real, but that it reveals reality itself. A universe of threads, woven together by forces unseen, bound forever in unity and tension. And in that revelation, we are changed. Every journey returns home, but never unchanged. We began with the illusion of solidity, descended into the abyss of quarks and gluons, endured confinement, seized illumination, and carried back the elixir of doubt. We have faced rival interpretations, uncovered philosophical cohesion, and glimpsed the invisible glue that holds the universe together. Now, at the journey's end, we arrive at a new equilibrium, not a return to certainty, but to a deeper balance. A recognition that reality itself may be forever bound by enigmas we cannot escape. In this new equilibrium, the gluon remains elusive, yet indispensable. It is both ghost and foundation, illusion and necessity. It cannot be freed, cannot be touched, cannot be seen in isolation. And yet, without it, the universe would collapse into chaos. This paradox is no longer a crisis, but a condition. To live in a universe bound by gluons is to live in a universe where the deepest truths are invisible, where reality is defined not by what can be held, but by what must be believed. This is the infinite bind. Quarks are bound by gluons, gluons bound by confinement, matter bound by forces unseen, and we too are bound by our limitations, by the reach of our senses, by the scaffolds of our theories. The infinite bind is not only physical, but existential. It is the recognition that freedom in the deepest sense may be an illusion. That reality itself is defined by binding, not by liberation. Yet there is balance in this bind. Confinement is not destruction, but creation. The eternal captivity of quarks and gluons is what allows protons to exist, atoms to form, stars to shine. Without the bind, there would be no universe, no light, no life. The infinite bind is not a prison, but the very condition of possibility. It is the paradox at the heart of existence. Only in confinement does freedom emerge. Only in binding does reality endure. This equilibrium forces us to reconsider what it means for something to be real. We have long equated reality with visibility, with touch, with direct proof. But gluons demand another definition. They are real not because we can isolate them, but because their effects shape everything we know. They are real not as things, but as relationships. They exist in their binding, in their invisibility, in their indispensability. Reality is not substance but interaction, not things but ties. In this light, the gluon becomes more than a particle. It becomes a symbol of the universe's hidden order, of the unseen forces that sustain existence. Just as gravity binds the cosmos, electromagnetism binds chemistry, and the weak force governs decay, so too do gluons remind us that the deepest truths are those we cannot hold. They reveal a world where the strongest forces are invisible, where the foundations of existence are ghosts. This is not a weakness, but a revelation. The new equilibrium also reshapes our place in the cosmos. We are creatures who crave certainty, who long for freedom, who believe in solidity. Yet the universe we inhabit denies all three. It offers us ghosts instead of substance, confinement instead of freedom, doubt instead of certainty. And yet, in that denial, it sustains us. It gives us stars, atoms, life. The infinite bind is not what diminishes us, but what allows us to exist. To accept it is not to surrender, but to awaken. There is a haunting beauty in this realization. Imagine once more the cosmic web, filaments of galaxies stretching through the void. Imagine flux tubes of gluons binding quarks within protons. At the largest and smallest scales, the universe is threads, invisible, intangible, eternal. We live in a woven cosmos, a tapestry of bonds. The infinite bind is the fabric itself, stretching from the subatomic to the cosmic, from matter to meaning. And so, the journey ends where it began, with a hand raised before your eyes. Atoms within atoms, protons within protons, quarks bound by gluons. What seems solid is a storm. What seems real is a web of ghosts. Your hand exists not because of substance, but because of binding. You exist because the infinite bind holds, and in that realization lies transformation. You are not a collection of particles, but a constellation of relationships. Not substance, but cohesion. Not freedom, but binding. This is the new equilibrium, to see reality not as certainty, but as paradox. To accept that the strongest force in the universe is unseen, that the glue of existence is intangible, that the truths we seek may never be isolated. To live in doubt, but not despair. To embrace confinement, but not as limitation. To recognize that reality itself is the infinite bind, and that in this bind, everything exists. And as we step back from the abyss, as the circle closes, one truth lingers like a whisper that cannot be silenced. The universe is held together by enigmas. Gluons may never be freed, never be seen, never be touched. And yet, they are the reason the stars burn, the reason matter exists, the reason we are here. Because in the end, to ask if gluons are real is to ask if reality itself is real. The answer is the same, yes, but never in the way we expect. The circle completes, the seeker returns, the ghost endures. And in the silence after the question, one thought remains. Perhaps reality has always been this way, bound forever by forces unseen, held eternally by the infinite bind. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.